With the James Webb Space Telescope sitting at the L2 Lagrange Point, people have asked me how would I calculate that distance, so I'm going to show you how to do it. So what we're going to work on here is finding the L2 Lagrange Point. We're going to calculate it, and that turns out to be the home for the James Webb Space Telescope. So here we have the Earth going around the Sun, and there are a number of Lagrange points. The one we're really interested in is L2. There's also L1, L3, L4, L5. The L2 and the L1 Lagrange points aren't really stable. You put something there to try to keep it there. You actually have to do some maneuvering to keep it there. The L5 and the L4 are stable. I don't think the L3 is very stable. So what we want to do is we want to determine the distance from the Earth for L2, that point, and L1, that point. But our main emphasis, what we really want, is to get L2. So here's a side view of what we have here. Now, if you put a satellite in the L2 point, it has to go around the Sun in the same period of time as the Earth. That's also true of the L1 point. It has to go around at the same period of time. So we're going to use the period of the Earth to help do a calculation. So what we'll start out with is we're going to use Newton's universal law of gravitation, which says that the force between two mass bodies, M1 and M2, is equal to the gravitational constant times the product of those two masses divided by the distance squared. So in our case here, what we want to first do is find out what the force is on the satellite sitting out at the L2 point. So this is a side view now. So the distance from the Sun to the Earth is R. The distance from the Earth to the L2 point is E for Earth. And the distance from the L1 point, I'm showing it as E, but we'll find out what it is. So this could be considered a different E. But they turn out to be very close. So we'll calculate the force on the satellite. So that's going to be equal to, the Sun is pulling on the satellite, so it's going to be the mass of the satellite times the mass of the Sun divided by the distance from the Sun to the L2 point, and we're going to call that R plus E. So it's this distance R plus this distance E, R plus E, and that's squared. We also have the Earth pulling on the satellite. So we have a second term. The second term is going to be the gravitational constant times the mass of the satellite times the mass of the Earth, divided by the distance from the Earth to the satellite, which we're calling E. So that'll be E squared. So that's our first equation. We can also say that the force on the satellite is equal to ma. So it's the mass of the satellite times the acceleration, a. So if we set this equation equal to this equation, what we will get will be the m satellite cancels out. What we're really after here is a. So we get a is equal to g times the mass of the Sun divided by r plus e squared plus the other term involving the mass of the Earth divided by e squared. So we want to get now another expression for A. And you know, if I have, say I'm standing here and I'm twirling a weight around in a circle, what is the acceleration of that? Well, let's say it's going around at a velocity v. The acceleration then is going to be v squared over the distance, we'll call it r. So in the case of the satellite at the L2 point, it has to go around the Earth at the same rate that the Earth goes around. It has to have the same period to make one complete revolution. So the velocity would be the circumference of its orbit, which will be 2 pi r plus e. That's the circumference. And we're going to divide that by the time it takes to go around, and that's going to be 1 year. We'll call it t. And that is all squared. And this will be, the r here will actually be 1 over r plus e. So this is what we're starting out with, and we put the correct quantities in. This is what we'll have. We'll have the circumference divided by the period gives us the velocity. We square the velocity, and we divide that by the distance, and in this case, the distance is r plus e. So if we simplify this, we have an r plus e here and an r plus e squared, so that'll cancel out. So we'll write it this way. We'll show it as 2 pi over t, that quantity squared, times r plus e. And what we'll do now is we'll set this acceleration equal to that acceleration, and we'll have gravitational constant times the mass of the sun divided by r plus e squared, plus the second term, gravitational constant, mass of the Earth, divided by e squared, and that's going to be equal to this quantity here. It's going to be the 2 pi over the period of the Earth squared times r plus e. So what we want to do is solve that for e. So if you look at this, you can see we have an r plus e here. If we want to clear the denominator over here, we'll have to multiply by an r plus e squared, so that'll basically give us an e cubed. E squared, e gives us an e cubed. We have this other e squared here. We clear that one out by multiplying both sides by e squared. We'll have the e cubed that we got multiplied by the e squared. So we're going to have an expression in terms of e to the fifth. So we have to solve for that. What I'm going to show you is a way to solve that by, what we will do is we will plot this side of this equation as a function of e, and we will plot this side of this equation as a function of e. All the other things we know in here. We know the gravitational constant, we know the mass of the sun, we know the mass of the Earth, and we know the time it takes the Earth to go around the sun. So everything is known except for e. And so if we plot these two terms and this term on a chart where the two curves, we'll get a curve from this and a curve from that, where the two curves cross, that is going to be our solution for it. So I'll show you that next. So we're going to graphically solve this equation. We're going to plot this side as a function of E, and we're going to plot this side as a function of E. And as I said before, where they cross, that's where the E is that we want. That's the solution to the equation. Before we get too much along, let's write down the expression for L1. Now, it's going to be very similar to L2, except L1 is on this side of the Earth, so the distance from the Sun to L1 is going to be R minus E. So we'll have a very similar term like this: gravitational constant, mass of the Sun, divided by R minus E squared. Now, the Sun is pulling the satellite towards itself, and the Earth is pulling it towards the Earth. So we'll have a similar expression for the Earth, but since the pull of the Earth is in the opposite direction, we have to use a minus sign. So this plus sign becomes a minus sign, and then we'll have the gravitational constant, mass of the Earth, over E squared. And that will be equal to, we'll have the 2 pi over T. At L1 point, the satellite has to go around the Sun at the same rate that the Earth does. So we're going to have the same T for the period of the Earth. And now the distance for the expression V squared over R, the R is going to be R minus E. So we'll have an R minus E here. So we have an expression for L2, we have an expression for L1. So here they are again. Here's the L2, which is what we're really after. Here's the L1, right? And in order to determine the value of E, we'll use these values. This is the value for the gravitational constant. This is the value for the mass of the Sun. This is the value for the mass of the Earth. I did add in the mass of the Moon. If you look at the Earth, its radius is something like 6,310 kilometers, something like that. If you calculate, and the Moon's out here somewhere, the Moon doesn't weigh nearly as much doesn't have as much mass as the Earth. So if you calculate where the center of gravity is, the center of gravity is actually around here somewhere. It's in from the surface of the Earth by about 1,700 kilometers. Because of that, I can add in the mass of the Moon. So it's this fraction, this part of the relative to the Earth, it's only 0.0123 times the mass of the Earth. So I've added the relatively insignificant mass of the Moon, mainly for completeness. Here is the period of the Earth going around the Sun. This is the number of seconds in a day. This is the number of days in a year. So this is the number of seconds. You multiply this out, that's the number of seconds it takes the Earth to go around the Sun. So we have all the numbers that we need. All we have to do is find E. So if we come over here now, we're going to plot our expressions. It's going to be A on this side. Acceleration, the units are going to be meters per second squared. So here's one of the terms. Here's the other term. We plot them as a function of E. And where they cross, if we draw a line down and read that, we get 1.51 times 10 to the 9th meters. So the L2 point is located at roughly 1.51 times 10 to the 9th meters using a graph. We can do the same thing for L1. Remember the expression for the L1, we have minuses where we had pluses for the L2. And so here's the one expression plotted, here's the other expression plotted, again as a function of E. And where they cross, that is the value for L1. And if you look at this closely, it's roughly 1.49 times 10 to the 9th meters. So you can see L1 is almost equal to L2. Now, we didn't include all of the factors, the effects of other planets and all that. We did not include all that. But this is a very good estimate for the value of L2 and for the value of L1. I'll show you now another way to solve for E. So as I indicated earlier, if you, or at least I meant to, if you clear out the denominators, you will wind up, like in this expression here, with an e to the fifth over here, in the same way for the L2. So here's the L1, we want to solve this. Here's the L2, we want to solve this. So it's basically e to the fifth that we're working with. That means we're going to have 5 roots. It's going to be in units of meters. And what I'm showing you here is the solutions obtained using Mathematica. So for Mathematica, all I have to say is solve this expression, put a double equal sign in here, and then the quantity that I'm solving for, and this is the result. So you see I have 1, 2, 3, 4, 5 values. There's only one real value. All the others have the imaginary number in it. And so this is the solution for L1. We had 1.49 on our chart. So it agrees nicely. And I do the same thing using Mathematica to solve this expression, again with the double equal sign here. And what we're solving for is E. And again, I get 1, 2, 3, 4, 5 numbers. All of them are complex, imaginary, have an imaginary I in it. And only we have one real number, and we get 1.511 times 10 to the 9th, which is in good agreement. So if we just look over here quickly, here's what we got using the graph, 1.51, very close to what we got using Mathematica. And over here, we got 1.49, again, very close to what we got using Mathematica. So the value for L2 is 1.5 times 10 to the 9th meters, the distance from the Earth to the L2 point, and L1 is 1.49 times 93 times 10 to the 9th meters for L1. And again, here's L1, and here's L2, and this is the E that we wrote our expressions to find. So I'll just summarize this now. So this is a summary. We really wanted to find L2. So again, we have the sun, and the mass of the sun is ms. We have the distance from the sun to the Earth being r. We have the Earth with a mass me. Distance from the Earth to the James Webb Space Telescope. See, that's my drawing for the James Webb Space Telescope. That distance is e. Again, none of this is to scale, and over on this side we have the L1 point. So James Webb Space Telescope is at LT, and the mass of the satellite, we'll just call it MSAT. So again, we use Newton's law of universal gravitation, and we put in the quantities. The force on the satellite will be this term from the sun, this term from the Earth, and the distance involved from the sun to the satellite is r plus e, and the distance from the Earth to the satellite is just e. And the next thing we did was we used F equals ma, Newton's second law. And so what we could say, the mass of the satellite times the acceleration a is equal to the same equation that we had here. So we have this force equaling this force, and that's what we're showing here. The MSAT A is equal to this term plus this term. The MSAT cancels out, and we're left with this for A. This is what we're going to use. We need the other expression, and that was from the A equals V squared over R, where you're swinging something around in a circle. It's going around at speed V, and the radius of the circle in this case is going to be R plus E for L2. So if we put in we want to determine the velocity. So it's moving out at a distance further from the Earth. So we have that as the circumference that it has to follow around. So we have 2 pi R plus E as the circumference, divided by the period gives us the velocity. We square the velocity, so here's the square. And then we divide by the R, which in this case is R plus E. This R plus E cancels that R plus E. So we're left with 2 pi over T, the quantity squared, times R plus E. So we take these two A's that we have, and we set them equal to one another. So here's the one side, and here's the other side. So this was our final equation for determining E for L2. So to determine L2, solve the equations for E, and we did that by plotting the left side of the equation and the right side of the equation to see where the two curves intersect. Or you can use Mathematica and get the result from Mathematica, or through our curves with 2 digits past the decimal point, we get 1.51 times 10 to the 9th meters for L2. So we found out what the Lagrange point L2 was in terms of its distance from the Earth, and that worked out to be 1.51 times 10 to the 9th meters. There are other spacecraft that have been out there. So we have the James Webb Space Telescope, which is out there now, and it looks in the IR region from 0.6 to 28.5 microns or thereabouts, and it has a very large mirror, 6.5 meters across. There was another spacecraft out there, Herschel, that looked at IR wavelengths from 60 to 500 microns, and it had a smaller mirror, 3.5 meters across. There was another one out there called Planck, however you want to say it, and it was looking at the density of matter, matter as we know it, and dark matter, and the age of the universe, and a few other things. And it was around from 2009 to 2013. I don't remember the dates for Herschel. And there was WMAP, Wilkinson Microwave Anisotropy Probe, and that was from 2001 to 2010. And then in the future there will be something called Plato, and I don't remember the date that's going to be launched, but it's something like 2026. So Plato stands for Planetary Transits and Oscillations, and it will look at stars to find out if planets are transiting them, so we'll know how many more planetary systems there are out there. So once the system goes through its life, they like NASA and others, they like clearing the L2 region. So I think a lot of the ones that aren't working now, they're put into a graveyard, a heliocentric graveyard. And I guess they eventually wind up crashing into the sun. So all the people who asked me how to calculate L2, I thank them for their question, and that's the value that we got for L2 using the graph and also using Mathematica.